So when we whenever we are trying to discretize any uh, transient problem, that is like this transient 1D heat convection, then we have one is the explicit scheme, and one is implicit scheme. So now first we'll directly jump into the implicit scheme for 1D heat convection, and then we'll see how the things changes when you do explicit scheme, and how are the things with Courant number. So there is one thing of that is Courant number is very important number. You must have heard about Courant number, right? This is Courant number, stability criteria. So whenever we are using explicit scheme, we are dependent upon the size of the time step. So in explicit scheme, this is how the delta t should be less than or equal to delta x square by 2 alpha. All right, this is the CFL criteria, and Courant number is this alpha. We should be always less than or equal to 1. So basically, this is CFL criteria, and Courant number is U delta t by delta x. So that is Courant number should always be less than 1. So we'll quickly jump to the test cases. So now, first, what we will do is we'll import. First, we'll import a scalar transform application from OpenFOAM to our application folder, where we'll make a solver for heat convection, 1D heat convection. So you all know that we can navigate through the OpenFOAM environment through WM project directory. And we go to applications, and then we have basic, no, solver, then basic, and in basic we have scalar transform form. Now we want to paste that to this area. All right. So what we will do, so we'll paste directly here, and we'll name this as my heat convection form. So one thing, whenever you are compiling your own solver, always make sure the name of the file, that C file that you have, and name of the folder is always the same, should be same. So for example, here the name of the folder that I am giving is my heat convection form. So this is for the convenience. It will be more convenient for you to compile it and use in the further process. So I am changing the name of this C file to my heat convection form, and also this name to the create field is as it is. There is no change in the create field. Now we'll open this. So this is the solver. This is the scalar transform. So now when we move into it, so it is here written that it is scalar transform form. So we would want to make this a habit, like whenever you are changing an application from the OpenFOAM and you want to customize it, you change everything. So make it a habit. You change the name of the folder and then name of the C file. Then you come here and you change here application is this, and what this application does, solve the 1D heat convection. All right. Heat
Abhishek,
convection. Mm-hmm.
is it okay if we first copy it, then rename it?
Yeah, first copy. Yeah, you can do it. No problem. So
Okay.
like you have to make sure that name of the folder name, like this is a good habit. Otherwise, you may get stuck. Like you have to see a lot of things. So you copy and then name it. No problem. That you can also do. This is a very basic Linux command. You can do these things, no problem. So I have named it, and it solves the 1D heat convection. Now we look at the create field, and first we'll have look at this. As I also told in the previous the previous session, that these include files point toward these libraries where there is source code which will help us in compiling this application or this code. that we have written in the main function. So these are uh, so these are supporting code that is there in these libraries, and this is the link to include file, or we can say the link to these files. Now one of the important thing is, so okay, so you will change here first. So this, in these files we have the name of the C file that we want to compile, that is my heat convection. All right. So if there is error like this, like my heat convection, then it will always give us a problem. So make sure you don't do these mistakes, like my heat convection form. One more thing is that you always have to add this form. So this is like syntax of the form, that if you are making an application, you have to add form at the end. All right. And always add a user app bin. So for app bin is situated where? So if I show you, so first thing is how to go to the application. So in Ubuntu, you can always go like this if you are familiar with the interface, that your OpenFOAM is installed into OPT, and you go to here application. So like what I was saying is, when you do this user app bin, your application will be saved in the your user location, that is this location application, uh, this platform Linux. So this bin is for the So this bin is for the all the application code that we have. So you see, there is 1D heat convection, 2D, whatever the application that I have compiled or whatever the solver I have made, these will find the executable will be here. So these are the executable for whatever we have compiled till now, application part. All right. In open form environment, so when we use user, it will go to this area, this part here. That is in our user defined uh, object files or compiled files. But if you don't use user, then it will go to here, platforms, Linux bin. So the thing is, we always want to use user here, because we don't want any changes to our main source code. So we don't want to modify it, so that like we don't get any problems in future. Because if you continuously keep changing your source code or the compilation of your source code, then at some point it will start giving you trouble. So it is safe always to do everything in user directory. So this will like compile and save the final compiled uh, object file or compiled file into the your user directory. All right. So let's now we'll move ahead in this. All right. So we were here. We were in application, and we had scalar. Okay, I'll rename it because I had some mistake. My heat convection form. Now it is right. And I also want to rename this my heat convection form. And now we will try to doubly make this. So first we should clean whatever already was already compiled. When we do this wclean.all, you see there was a folder here already, which is not here. So it will generate as soon as we compile it again. So make a habit whenever you are copying a new solver, first change the name and compile it. So you are doing any changes to the solver at every step, you should compile it, because let's say if you're doing 10 or 20 changes and then you're compiling it and it is not working. So that becomes very hard to debug. So we'll go step by step and do changes. All right. We'll open these two files now. So this is create field. So as I will not go because I have already explained what these set root cases, create mesh and create time does. And this create fields points to this file. All right. And then we have this. So point the thing is this in heat convection, we only need we only had two files. So we have, as I explained earlier, we have DDT of like time derivative, and then we have this one. We don't have this Laplacian. All right, that is diffusion term we don't have. So we'll first remove this diffusion term. And FV option for the is for the like if you want to add heat generation to particular area of the cell, or if you want it is like advanced utility, not utility I will say, but it is used when you want to give time dependent or a coordinate or like you time dependent or coordinate dependent heat generation or any source term, or you can do a lot of things with FV option. So we don't require it here. So we just remove this part. All right. And because we don't and one more thing. So here FV scalar matrix is defining how the T equation looks like. That is how the AX equal to B matrix looks like for the T equation. But because like you can always do like this that like you first define the matrix, this matrix, and then you do T equation dot solve. You can always do like this, or you can do this. That is solve. Directly you write solve and you can comment this out. But for now, let's go by this. Okay. So now let's compile and let's see what are the errors that it is giving us. Okay, so but it is not giving us any error because we have just removed some things. We have not added anything. So here we have volume scalar field T, volume scalar field U. So in last lecture we were doing, so we should remove create FV option. This is because it's just beginning of the modifying your solver, so we'll not go into the more advanced things. The last time what there was I was giving is, so U here is volume vector field. So from this volume vector field, open forms make the fluxes on the faces. So for open form, fluxes on the face is very important if there is convection term. So in convection term, we have like in convection term or in advection term, we'll say the phi that we have is on the fluxes. Also in like in your Navier-Stokes equation. So this hash include create phi dot com. Sorry, create phi dot h makes calculate fluxes from this U field. So this is vector field. This is volume vector field, and this create phi dot h makes fluxes on the faces of the control volume from this. All right. So the last time we were not adding this, that's why we were getting the problem or error. So now we have modified almost everything. So create field T, yes, U, yes. So we don't need this diffusivity part. So you can comment this out because we don't have diffusion part right now. We'll compile this. Okay, so we'll move ahead. It is compiled. Now what we will do is we will go to a run folder. We'll copy any test case that we have. Probably we'll copy. So we have already made some test case. You can see this pure convection test case I have made. but I want to show you from the scratch how can you copy a test case and modify it. Okay, so what we will do is we'll make folder new, and this you want to copy a tutorial, all right? Which tutorial? In compressible simple form. So what will it WM? Sorry, CP minus R. Then we have OpenFOAM. Sorry, it's not tutorials. Now we'll do this. You can always tab and you'll see it is small t, and then we go to incompressible, not that. Then you see here, incompress small, then you go simple form and double tap. Let's go to the ICO form, all right, because we want ICO form. Then we want cavity, all right. And you want to save it here as, let's say, pure convection. Pure convection. Okay, so we have now copied the which case? Cavity case to the pure convection. So I'll open things in parallel because we don't want to spend too much time in changing things because I have already changed them. So this is the pure convection. This is the pure convection folder that I have already compiled. So I'll just quickly go and block mesh dict file is here because we have to define. So what we are defining here is uh, on the left. Open it. So what we have here, block mesh dict here. So we have top. So we only have one block, and we have 1D 1D heat convection. So we have like 100 cells in X direction, and only one cell is in Y and Z direction. Now on the boundary on the top, we have patch on the bottom, in, out, all right, and we have front and back that are empty. So we want to copy this block mesh dict to our new file, all right. Now we have made mesh. Okay, we have changes the mesh. Now in the same way, we have to change. So we the one thing is there that there is no pressure. So we don't need, because we are doing only heat conduction, heat convection. There is no pressure. So we'll copy the temperature and we'll open it. So in temperature, you see, you just have to, like you can also edit the pressure yourself, pressure boundary file yourself. You have to like change the dimension. Internal field is uniform, and in object you have to, instead of there it will be P, and when you are like initial condition for temperature you have to write it as T. On top we have zero gradient, bottom we have zero gradient, and at inlet we have fixed value, and the outlet we have zero gradient. So the boundary conditions are, on the left we have some temperature given, on the right and everywhere else there is zero gradient boundary condition. And for the U we have like for the U okay, for the U the like U is constant, U is not changing at all, because we are only studying convection and we are not solving momentum equation here. There is only a 1D heat convection equation that we are solving, so we don't have like so so we have constant velocity throughout the domain. So you see at top and bottom that is zero gradient, front and back is empty. At inlet we have one velocity and it is not changing. All right, so we'll copy this to this folder. So now we have what we have done is we have changed the block mesh dict U and T. Now we'll go to the application part that is more important, main important thing. So now system folder. If you go to system folder, we have control dict. So in control dict folder, what you have to do is you have to change this to what was the name? My convection. My convection form. So if you are forgetting the name, you can always go here and look for the name. The name is my heat convection form. All right. So you do changes here. My heat convection form. All right. So this is now you start from zero. That is start time. Start from start time. That is zero. Stop at end time. And end time is 0.5. This is delta t. And this is time step and other things are here. Another write interval, that is you write after each every 20 time step. Purge write is something if you want uh, purge write is that I think it is when you want to write only the last term, only last time step, not the intermediate one. And these are time precision, write precision. All right, so we have done this my heat form. We have changed this. Now we'll try to run and we'll see what are the errors that it is giving us. We'll try to run this pure convection block mesh. What was the name of our solver? This was the name of our solver. All right. Keyword simple is undefined in dictionary. Okay, so it is, you see, it is giving us some things now. What it is telling us is to in our when we are like in our solver, we have used simple loop. So simple loop is it like you can always use a for loop here, but like everything is defined in the this simple loop. All right. So when we use simple loop, it like continuously change until continuously solve iteratively until we get a steady state. So error was simple loop is not defined. So we are using simple loop here, but the test case we have copied is of icoform. All right. So test case we have copied is of icoform. If I open FB scheme 7 FB solution, what you will see is here it is only have defined only the piezo algorithm. So in our case, in this case, piezo algorithm. So what we have to do in these cases is you have to go to the simple form and see how FB solution is defined there. So now we'll go here, open form. We'll go to application, not application. We'll go to tutorials, incompressible, there it is. And we'll go to simple form. Simple form here. You can open any one, let's open page daily, which is mostly used. And we'll open FB solution for this. You can see here the simple loop is defined. So we can because we have copied a case which use piezo algorithm. The simple algorithm is not defined here. So what we will simply do is we'll copy this simple part and we'll remove the piezo and do this. All right. Now simple is defined. All right. Now what it is running, but it is saying something that keyword divergence phi t is undefined in the dictionary. So what is this? Because in the FU solution, there are first we define solvers, solver for p variable, p final pu, but we don't have p as a volume vector field or scalar field to solve. We only have t. So what we do is we remove this p and we add t, right? So it is what it is saying solver, you are using a smooth solver. The smoother for the solver is system Gauss Seidel. So these are the attributes and tolerances 10 is to the minus 5. And here it is telling you that uh, simple loop, non-orthogonal character is 0. So all these details will be covered in future, like when we go deep into the solution part. And here is the relaxation issue. You don't need not give relaxation here because this is very simple problem for now. But you can always like give it no problem in this. Now let's try. Now ill-defined primitive keyword Z. So line 42. I have something ill-defined here. So yeah, one second. This sorry. So in simple also you have to remove this P and T. You have to define this field vector as T, or sorry, the volume field as T. That was the problem here. Now it is saying phi T is undefined dictionary. FB scheme. So there is also some things in FB scheme. Now we'll go to the FB schemes. Yeah, so in FB scheme also there is grad of P we have to change to grad T, and this phi we have to change it to T. So basically if you are like changing taking a case or copying a case which is different using different solver using different Laplacian divergence schemes or basically different variable, then you have to change things. So now you can see this is compiled. All right. Now we'll open Paraform. Let's see how it looks. So U will be always be constant. You see U is always one. So there is no change in U. But the change is occurring in. So you see at the in the first time step we have at the right that is temperature 1. So now the advection begins, temperature starts moving and it has reached to this point. All right. So if I go to the control dict file, I think it is right. Yeah. If I go to control dict file and I change the time step as 1, not end time as 1, and rerun the solver again. Let's, let's quickly do that. This is a very simple problem. It will build the basics how to make your own solver and how to select the case, how to change the test case according to that. All right, so let's see the temperature. Now temperature has reached little bit ahead now. Okay, one second. Temperature has reached little bit ahead now. It has solved. Okay, so we'll try the case and let's move ahead. Now what we want to see is the next task is now we have made a solver. So in conduct convection part, what more important is like Courant number, how the things changes when we change the Courant number. So we'll see the effect of Courant number. Okay. So the thing is, yes, let me also show you this. So for post processing part, let me add one thing to this that I have like so here you have seen that. So here you have seen to ParaView that how the temperature is varying, but we can also use some utilities. So utilities are basically function objects which we can use for like post processing part. So for example, if we want to see profile at the midsection or profile at okay, so we want to see So what we want to see is we want to plot using the utilities that we have in OpenFOAM. We want to plot at the midline, and like we want to extract the data at the extractor data or flow field from the like flow field, that is temperature. We want to extract the temperature, right? So this is one utility that we have, that is single graph. Okay, so utilities will be covered in depth. Okay, then we'll move to the function objects. But for now, we'll quickly see how things is. So actually, I have already done it. So I'll just run a case and get over with it because it is taking too much time. So we have form clean tutorial. Okay, now we'll just block mesh, and we have our solver, that is this solver we have. Sorry. We have my heat convection form. Okay. So now, so there is also a README file here. So you can see there is the README file is here. So what we have to do is we have to run a command to extract the data using that uh, utility that we have here. So in this utility, basically we have what we have defined is we are defining a single graph that is it is a line start from this point and end at this point, and we are want to extract the field T. And this is interpolation scheme, that is cell. We want to extract the cell data, and set configuration is that is we are extracting in x-axis, right? So the point is, so how to the thing, most of the time when we have utilities, we don't know the command how to use that utility. So for that, so this utility has been used in this plate hall structural solver, and it has, when we go to all run of this, it has given the command. So you see the command is here. The command is like this: post process minus function single graph. Okay. So what we do is we type this. We have copied this command. We type it and we run it. So you see, it is saying at every time step it has like extracted the data. So we go to post processing single graph. You can see the data here. Not this one, sorry. Pure convection post processing single graph. So I had written a GNU script, but I am not finding it right now. Okay. Thing you can do is you can also always do like this. So you go to GNU plot, you do plot 0, single, and whatever T inside 0 we have line. So line with line. So you see it is giving us at 0 times 10. Now if you do replot, that is 0.1 time step line with line. You see gradually that the temperature, that is the temperature is moving ahead. So if I plot the last time step, it has reached somewhere here. All right. So it is moving ahead. So you can always use the function object utilities to do these things. All right. So now what we will see is Okay. So now this is finished. The next step is we'll add next step is to add conduction and heat generation to it. Okay. So so what we will do is we have already made a test made this solver. So according to that solver, we have to do changes to this. So now we have solve the heat convection, and in heat convection we want to see the effect of Courant number. Okay. So actually this I have already done all these things. So I'll just show you guys everything. The point is the Courant number is important. So in simple form, Courant number is important, like how many time steps, or you can say some, you can also call time step as iteration in simple form. How many time step it takes to solve to get to the steady state, or how many time step it takes to solve it. All right, give me 2 minutes. So the thing is, I have made these test cases in which have different value of like uh, Courant number. Okay, so you can see here I have Courant number which is like Courant number of 10. All right, delta T is zero point 0.1 and Courant number is 10. And then we have we are doing these changes to the control dict file only. And then we have in this case we have Courant number of 0.01 time step of 0.001. So you can see like this. So delta T U is 1. This is delta T divided by delta X. That is our Courant number. So it is 0.01 in this case. So all these test cases that we have here are for different Courant number. And the similar way that we have done for the previous one, we do the same thing. Everything is same as we have done in this previous test case. So I'll just there is nothing that I have already done yet, so I'll not rerun it again. I'll not run each case because it will take time. So same solver that we will use here. All right. The name of the solver was my heat convection. Okay, okay. So this is not. Give me a few minutes to adjust my cases. Just 1 minute. CF value. Okay, 1 second. So the thing is, so what we have, what there it was giving us is, so you want to see the effect of Courant number, right? So what we do is here is go to control dict file and you change this solver as solver my convection form. Okay, and we run it now. Dot mesh is already there. So now it is run. In similar way, we have to run each and every case. I think most of them are already run by me. So you see, and we have in the similar fashion in the previous one, I have extracted the. So in this case, what I have done, one thing is that I have extracted only the latest. So I have extracted the velocity on the center line for the latest time step. So this is the command post process minus function single graph, and this is for the latest time. So when you do this underscore latest time, it will extract only for the latest time. So what error it is giving is latest time is it is error. So latest time. All right. Protect. Okay. Sorry. So latest time. Okay. Now it is compiled. So now I have. So I'll be sharing each and every of this test case with you. So you guys need not to think too much of how to run these test case. This is very simple. Similar way I have uh, run every test case that you see here. And then there is GNS script that I have written. So what this GNS script is does is it plot the velocity profile at the last time step. You see 0 point, that is this case post processing single graph 0.5. So this is the GNS script you can have a look at. And if like I run this GNS script, okay, it is run. Now what the output of GNS script is cfl.apis. It is just output. So you can see that as we are removing, increasing the, so the analytical solution is what? Analytical solution should be a straight line. So because there is no diffusion, so as the velocity moves ahead, temperature should move ahead with it with exactly a straight line according to analytical solution. But because of the Courant number, there is always like because of the Courant number or the time step that we have, there is always a like region of gradient. So you can see for this as the Courant number is increased, it is more approaching towards the sharp drop, that is analytical solution. All right. So this is it. I'll be sharing these test cases. So in similar way, we have test cases for if you want to test like if you want to test the schemes part. So you can see the you, I think you if you have done like read CFD, you must have heard about the phenomena of false diffusion, and that occurs in convection term. And for that, most of the time we use this upwind schemes and linear upwind or quick schemes. All right. So most of the time we use these schemes. I have similar way I have run these cases. This case is not run. Let's run it. Was it? You see in post processing, single graph, there is 0.5. Now just and okay. Now run the quick scheme. You see, quick scheme is converging so fast. One thing. Latest time. Now let's you see how the GNU file gives what GNU file gives us. So it is giving us output.cfl. It's not CFL, it is. You can see when we have there is some issue. One second. So let's plot it similar. So this GNU plot files you can always change. But for now, let's do like this. We have 0, 0, 1 upwind. Then we have in that post processing, there's single graph, post processing. Okay, so in this, all right. Now you should see single graph, single graph, and then line. The single graph you have 0.5 with line. So this is how it is looking for the upwind scheme. Okay. Now if we replot it for, let's say, for quick scheme. So basically the first order of wind, second order of wind, and Q scheme is also second order. So this basically we are using the more order discretization for our convection scheme, convection part or advection part, more specific. So you can see there is, although there is not much change because this is not a very heavy simulation, you can see a change in the QCAT upward. So you can see the uh, Q scheme is giving us this dip. So there will be always changes in the like when you change the scheme, there will always change in the solution. All right. So upwind seems to be giving us better results. So this can also happen in few times. So like you can, I'll give you the test cases. You can do permutation and combination and see how changes. So what thing that we have changed here is in upwind scheme is you go to in system folder in FV schemes. So these are all the schemes for uh, divergence part. So here you are using Gauss linear upwind. So you can use either upwind, linear, quick, limited Smith. So there are a lot of schemes. So you can always try these things. Now we'll move ahead, and what we will do is now we'll solve a scalar transport. Okay, so there is my scalar transport form that I have already made. So difference between this and this heat convection is I have added these two terms. I have added these two terms. All right. So in this tutorial, I will also show the significance of finite volume method and finite volume calculus. So what the difference is, I have already explained earlier, but I'll also take you through this once again, just to give you a quick recap. In finite volume method, what we have is, so this is our 1D scalar transport or 1D heat convection conduction equation. And when we do with the explicit scheme, so see in explicit scheme, whatever we accept this time temporal term, everything is recorded at nth, like the previous time step. So you can see that when we get the final equation, we have only Tn plus on the left hand side, everything else is goes to the right hand side. So makes that is we have like Ax equal to B. So everything that we have here is goes to the right hand side. That is n terms. So when we use FBC, the things are getting added to the B, that is of the Ax equal to B. So we are solving Ax equal to B, uh, B matrices. And when we use implicit scheme, how we discretize is we discretize like this. So this conduction term is getting discretized using this n plus 1. That is, we are considering the temperature at the current time step or the time step that we are solving for. So in this case, most of the terms come to the left hand side, to the x part. So and these terms are like coefficient of the A. All right. So in the implicit, things are getting added to the coefficient that is A, and in the explicit term, things go to the B. That is that we already know the right hand side. Okay. So now we'll go here. And for now, first we will do with FBM. There is nothing, no change here. So we have just added this Laplacian, that is conduction term or diffusion term, and Q is the heat source. And in the create field, I have create field, I have done nothing, but I have added Q, that is heat generation, and I have again uncommented this part. Which part? I have uncommented this input output directory, that is transport properties. I have to again read from the transport property, that is DT, diffusivity and the heat generation part. So these are the changes that I have done. Just to show you, this my scalar transform is already compiled. When I'll do wmake, is not compiled. Okay. So let's, it will take a while. So it is compiled when you do wmake. So where it is going, my scalar transform. If you want to look at where the compiled or where the source code is, like compiled code, object file, you can also say it, platforms. This, if you go to bin, you will see my scalar transform form here. So there is my scalar transform form. So you can always see file is made here, like where the file goes. You can always look at these things if your solver is compile properly or not. Okay. So now we'll go to the run folder. Now I have already here like make a test case. So previously I told you how to copy a test case, change it according to you. And I'm not gonna do that again, that because this is again the same process, because I have already had a test case. What I will do is I'll clean it and show it to you. Okay. So if you go to system folder, what changes we have to do is simply these. First change is we have to add this pure convection, not pure convection form. One second. We have to change this. Make sure the name of your scalar transport is always actually second. So what was the name of this? What name was this? My scalar transform. Better to do copy paste. First, we have to run block mesh. It's done. Now we run this case. You see, it has run until time step 2. Because now, so we have run it. The thing that we have to change in this, we had to change in this was control dict, and nothing in the schemes. There was no change in the scheme. Temperature is all is as the same, and we have solution. So there is no need to change anything. All right. Rest of the things are as it was previously. The thing that we have to change is one is in this. For example, in previous case, we didn't had this DT. DT was diffusivity, and these were the uh, like these were the signs, or you can see SI unit of this and Q. So you have to add this diffusivity and heat generation to this. So heat generation I'm adding as 1. Okay. So let's quickly go and look in the para form. So now it has moved ahead. Like you see, uh, at the last time step, the temperature is up ahead. Like it is moving ahead, and it because we have added a heat generation part. Okay, so we'll better see it using the line plot. Okay, for the line plot, what we'll do is we'll do this. Yeah, this not latest time. You want to see at each time. Okay, now it is done. Scale it up. Post processing. Single graph. Ah, actually, I deleted the Geno file again. So let me copy it from here. So when I'm doing this from clean tutorial, it is also deleting this script file that I have. So I'm gonna copy it outside first. Okay. So in the similar to the previous case, now we have this timestamp and we want to see how the velocity, so temperature profile is evolution with time, how it is happening. We'll do the script file. Is saying cannot open this. Okay. Let's see what it is. If we look at the script file, sorry for this. We were here, okay. Post processing, single graph, gene script. 0.4 we have to change here, 0.8. The time step is changed now. 1.2. We have 1.6. You can always add an extra with this line type 6. Line type 6 you can add from here. So Gnuplot is very good if you want to do things like this. 6, what it says. Uh, this is 2. Let's again run the Gnuplot file. Now it is running okay. And it is giving us temp.eps. Uh, so you see, actually the Gnuplot that was deleted was well looking, but this is not the Gnuplot that I have finalized. But you can see that for the 0.4 time step, uh, 0.4 time step, you can see uh, it has not reached a steady state. For the 0.8 time step, it is reaching towards that. And 1.2, 1.6, and 2 are all overlapping. So means after zero point 0.8 around 1, it has reached a steady state. All right. So this was using finite volume method. All right. So if we are using, let's say, calculus, so you can always do things like this. Okay. So now we have this test case here. Okay. Now what we will do is we'll do the same thing, and now what we will do is we'll change this divergence phi to C and this also to C. What will this do is this will use an explicit scheme for this convection term and also for the uh, this conduction term. So we will go to this application. Where was it? Week 4, my scalar transport, and we'll do W make again. What we have done is we have changed this to FPC and FPC. Now what we want to see is how the things are changing when we run the case. Let's copy it. Uh, that- What we'll do is keep a copy of this post processing. Now rerun, let's like form, just clean everything. I have kept a copy of the previous file that is post processing. Let's run block mesh and then what it is saying. Okay, so there is some problem with this. It is saying that, so let's remove it. And rerun this again. Block mesh. I don't know how it is affecting it, but now we'll run my scalar transform. Okay, now it is run. Now we'll extract the velocity profile at the center. It is done. In the similar to the previous way, and we'll open this temp. We will see how things changes with the FPC part. Okay, that is the main target of doing this. Now if I run Gnuplot here, it is, you see, so what is happening, you can see by it yourself. So the thing is, it is diverging too much. Okay, it is not stable at all. So to make this stable, you have to reduce the time step. So the thing is, uh, the finite volume method, that is implicit scheme, is stable irrespective of the time step. Okay, so you don't need to define a Courant number for it. But for the FVCs, when everything we have on the right hand side, we have to define the Courant number. So the physics of this is very simple, that when velocity is moving through a one cell, it's at a one time step, it should not move from one cell to another. So it should spend more than one time step in one cell. So that is the basic of the Courant number. So let's try. Now what we will do is, I just compare the two. You see, if I compare the two, in the implicit part, that is FBM, it was solving everything at each time step iteratively. So at each time step, we were getting the exact solution. All right. So the transient response for this case was perfect, but in this case, it is diverging. So it will give us somewhat of good transient response if we reduce the time step. So let's do that. The implicit is stable by default, and it does not, like, it is not, we don't need to define Courant number for this. Now what we will do is we'll quickly change our time step. Let's change time step to 0. Then the Courant number, let's comment this out, and now the Courant number is 0.1. But there is also heat generation in it. So one thing. Okay, great. The right interval is okay. Oh, my skeleton. You can all like you need not to do this clean tutorial because in this case the file that will be made will be overwritten. I have done in this case, but you need not do this every time. We'll copy this script file. First, we have to do that. Extract the data. Okay. Now this is the correct genome file. Now let's see. Now you can see when we have increased the time, like decreased the time step, it has like it is better than before. Like it is more like implicit. So the FP scheme is very time dependent because everything goes on the right hand side. But in so you should look into these how we discretize into FVM and FPC. All right, you can to look into these. Okay, so uh, I think everything is understood now. If you have any question regarding this solver, this 1D heat convection and this scalar transport solver, then you can ask now. You guys don't have any questions? Okay. So I'll be sharing all these folders with you. All right. So now what we will move ahead is we'll move ahead with the boundary condition. So next part is how to change boundary condition. So what we'll do is we'll look into this. We'll try to change the boundary condition, but we'll copy a boundary condition folder from the OpenFOAM directory and copy in our own user library, and then we'll compile that library and try to use that modified boundary condition into a test case. And for now, we'll go with this parabolic velocity profile in 2D channel. And tomorrow I think Pratish will be covering this paraboloid velocity profile in 3D channel. If we have time, we'll cover this also for now. So let's quickly start this. Okay. So what I want to show you is uh, this function, this boundary, the boundary at the boundary, whatever we boundary condition we do is using FB patch field. So we had every boundary is a patch, and we have to define a patch on that a field, like a field that is either constant or variable on that patch. So everything that we have to do with FB patch field is in this is comes under the FB patch field. So we'll look into where the so one thing yes yesterday one student asked me so how to like search for any file. So for any file we can search using this find name and then name of the file. Let's say uh FB patch field. I hope there is file with this name. No name. FB patch field dot h. Hmm. Next. Like if you know the name of any file, you can search by using this. And there are also a lot of permutation and combination to this command. Like you can, for a file, simple file, you have some other extra thing. Like I think it is something like file minus R or minus C or something like this. Or if you have only simple file. So these things you can always look into. Like you can go to Google and search like. So yeah, like if you want to search for any file that you know the name of, this will do things like, let me think of a file. Just search anything from here like pcd.h. Search. Actually, I forgot the exact syntax of the this command, but you can use these things. The people who are day and night I use OpenFOAM in their research, they should be familiar with all these kind of commands. So you can always like talk Pratyush because he has extensively worked on OpenFOAM. I don't remember that command exactly. You should Google all these commands and use actively these commands so it like to make things more smoother and takes less of your time. So we'll move into where like, so now we were moving to the FP patch feed source library. That is, in my case, it is an OPT. So you can always like browse through the terminal also if you're familiar with it. You just have to use WM project directory and you can go through that. So now we are in the source library. Now what we where we have to go finite volume. In finite volume, we have these function objects. And these function objects we'll discuss later. For now, we have to go into fields. And we have this FP patch field. So the patch, whatever patch we have defined for the boundary condition application to apply the boundary condition, everything is defined here. So you have your surface field, volume fields, the definitions are here. Now this is FP patch field. So when you go and you see the basic FP patch field and constraint derived FP patch, this is the main library which controls everything. Okay. In basic, you can see calculated couple, direct, fixed value, mixed slice. So these are the basic boundary condition which you can use. And so basic, and these are the constrained boundary conditions, cyclic jump, cyclic empty. And these are, I think these are related to MPI, I think. This is symmetry boundary condition, wedge boundary condition is also there. So there are different boundary condition you can always go through. And if you want to, if you just casually look at the one of the boundary condition, so what it says is this boundary condition enforces cyclic condition between a pair of boundaries. All right. So between a pair of boundary, there is cyclic boundary condition. So the patch name, so type you have to define it cyclic. So in if you go down, it is always asking for a type name. That's cyclic patch type name. Cyclic FB patch. So the thing is, you have to add this thing. Example. So when you're going to boundary condition, you have type as cyclic. Okay. Nothing more. You don't have to do much things. So for now, we'll go into the derived boundary condition. So because you have not, you don't guys don't know how to compile a source library from scratch. So I'll just give you a tutorial how to like copy one of the derived boundary condition from here, take it to our folder and make this as our customized boundary condition. So in this also you can see, so there are different things. So these are the fixed boundary condition, fixed profile, and then we have different kind of boundary conditions. There are some boundary condition which changes with the with time also, or they're like sinusoidal boundary condition that we will be covering in the next. Okay. So for now, what we will do is we'll pick any boundary condition. For example, let's pick this free stream velocity or in free stream velocity. Let's pick this boundary condition. We'll copy this. We'll go to this. So now we are not doing anything in the run folder. Okay. So we have to move from the run because this is not a this is not an application or this is not a solver. This is a library. So I have already made a lib folder in which I'll be copying my copying this free stream velocity boundary condition. So again, the one thing is important is as soon as you copy everything, you start changing everything that is there. Because sometimes you may be lazy that I don't want to change everything from folder to C file to .h file to everything, but whenever it will start giving you an error, just make it a habit. It will be more better. So I am doing this my free stream boundary condition. All right, my free stream boundary. I am copying this. So when I am opening this folder, when I'm opening this folder, what I will do is edit, search, replace. What I will tell is this is replace everything that has a name of a free stream bounding condition with free stream bounding condition. So I have taken this as case sensitive, otherwise you'll be in trouble. So this is case sensitive. I'll change everything in this document. I've changed everything. Okay, similarly, I'll change this everything in document for .h file also. Okay. So now the one thing that is to be like that thing that is different from the compilation of a solver is we don't have a make file for this free stream extra make file. Even we don't have make file here. We don't have make file here. All right. So for these things, so you keep going backward and backward in the folder, and wherever you get the latest make file, you just copy it. Because in this make file, by default, all the libraries that are needed for this will be there. So we need not change much of the things. In this make file, if I go here, you see there are so many C files, but we don't want this much of C files. We'll just simply restream. Just remove everything. Just remove everything that we have and what we write, change this with my free stream. I think free stream is not okay. Anyhow, we should have picked like different case, I think, but it's okay. Free stream is not like constant boundary velocity, so it's okay. Free stream velocity. Now, one more thing. As I have said, you have to always put it in user. So when you put it in user, so when you put this as user, the things will go here where this platform, this will go into libs. So you'll see SO files. My stream, my free stream velocity FB patch field, I have already like compiled here. So when I'll compile this also, it will go to this library. If you don't use this user here, it will be added to the uh, it will be added to the OpenFOAM platforms here. And you don't want here. I don't want this because you you want to keep everything in the user directories, whether application solver or your test cases. Okay. So now let's W make this. It will go through us a lot of errors. So first W clean dot all. Okay. W make was it mm, minus help. So when we type W make minus help, so what will this do is it will tell us everything about the W make, how we can. One thing is W. So here you can see that the lot of things that you can use. After W make, you can use exe, which will compile statistically linked executable. And then if you do W make lib, then it will compile statistically linked archive and compile statistically linked libo will compile statistically linked libraries. So the for our part, so we want this compile using dynamically linked label library. Okay, because we want again if we are using any of these or this, it will do changes to the our source code. So we do not want that, and we want our libraries to be accessible dynamically. We want the dynamical linking. All right. So we will go ahead. So if you have regarding this, you have more questions, you can ask Pratish in the next, because this is because I don't have much information about this, but these are the things that you can do with wmake command, because we are doing like compiling a library here. We'll go with the wmake libso. All right, let's see what it is saying is linking include no rules to make target. Okay, let's see what it is. Ah, yeah. So on files, okay, files I have named the C file as .c. Okay, so I want, so we have to change this accordingly. Okay, my free stream FB patch field, and I want to copy it. So if you practice this one or two times, you'll be familiar with it. So this will not be of much issue. So what I want to do is the problem was it was not finding the C file. The name of the C file was not there. And my free stream velocity FB patch field. Okay, I am naming this library as free stream FB. So in this lib file, I want to delete this. I want to show you when we like compile it, it will go, it will be observed there. 1 second. It's still giving me this error. 1 second. No, it is not giving me that error, but it is giving me a lot of others error. What it is saying is, 1 second. I freeze string velocity. 1 second. 1 second. If you guys know the answer, you can also like actively participate. What you have to do is we have to go through everything one by one. Okay, copy this, change the name of the folder as my free stream velocity FP patch vector field. Okay, then rename it. Okay. Mm-hmm. Then we rename this, and in the make file, okay, start. Now let's doubly make. So still saying that oh, okay, should be capital C. Okay, now it is coming. So you have to make sure everything you are like the name and everything should be correct. So what it is saying that fp patch field dot h is no such file or directory. Okay, so let's see. Hash include fp patch field dot h. Hash include means. So there is some, so why it is saying is, so what the error it is throwing is that, so we have a class that we are calling is that is fp patch field dot h, but it is saying that it is not there. Why? Because it is not able to access the library where this library is, or where these library files are there. So here we don't have a finite volume library is not defined here. So we'll look into the previous cases. I have already done this. So I'll quickly look at that, like which file we are missing, options. So you are missing this finite volume. So we'll just copy. So you are missing this file. You see, in this option, we don't have this finite volume. So these kind of things you have to make sure that files that are required by you are defined in your like are defined in this option folder, option file. Now it is throwing us a lot of errors. Okay, let's just clear it and see what is. What it is saying is my free stream velocity namespace form does not name a type, because yes, because we have not done changes to the this file, that .h file. So we simply do these changes by search replace, and we'll paste everything in the document, and let's see if it compiles now. I think it will not still give us some issue. I think now it is compiled. Okay. So now how to use this? Now you have seen what are the changes we need to do. So I have not done no change. I have just copy a folder and make some changes in it to use it as our customized. Okay, so now we'll just quickly go to a test case. I have already made one more thing. Now you can see this is successfully compiled. So we have my free stream velocity FB patch vector field dot so file generated in this platforms library. All right. So this file generation means it is successfully compiled. Uh, Now I want to quickly show you. Okay, so I have already made a test case, which is which one? This one, yeah. I think this is this one. Okay. So in this case, how to use? What are the changes that we have to need to do to use that? To use that customized boundary condition. So this is the test case, simple piece daily test case of simple form. On clean tutorials. Now block mesh. So it does not allow any copy kind of folder things to inside. I don't know why. Okay, so let's just remove this block mesh. Okay, you want to throw it out. Wait, delete. First one now, block mesh. So what changes we have to do is we have to do the first thing is now you have compiled a library. How will this test case know that I have to use that library? Because it is not directly linked. So for the customized library that you have made, any customized library, you have to like define those library during the runtime. And runtime is controlled using control dict file. So in control dict file, you have to define the libraries like this. So I have already defined these libraries. So you see, I have like when I made these test cases, I defined different libraries, and I am all like telling the test case go to that when the simulation runs, go to these libraries and keep linking with these library. Okay. So first thing is you have to define these libraries object files, SO files like this in control dict file. Second thing you have to do is you have to change. Okay. So let's delete all these things. Second thing you do is you have to change the U and T file, U or whatever the files you have, U and P. So P, we are only changing for the T, we are only changing for the U velocity, that's the velocity profile. So we only need to change that. So the thing, one more important thing is how to identify which type of boundary condition is this and how this free stream value I have given. So the thing is whenever you see whenever you have a object for sorry a library file. So this my free stream velocity FB patch field is a class that is and public we have a type name and that type name is my free stream velocity. All right. And these are the constructors, all constructors. So this is kind of polymorphism that for a single constructor that is my free stream FP patch you can give different inputs. For example, where we have two input that is from patch and vector volume or patch and mesh. Here you also have a dictionary. Okay. So in this dictionary, you are passing these three things. No, it's not passing. So this is a dictionary. We'll look into this in the .c file. And these are all what? These all are like constructor, different constructor. And these are the member function which are used. And this is the main function virtual this. Okay. Now if you go to the C file, so you so the type of boundary condition that we have is my free stream velocity. Okay. And if you go here, so in the type will type which the type of boundary condition will type my free stream boundary condition. And the next input that we want to have is we want to assign a value. So if you look at my C this FE patch will write will see a value. What is the free stream value? Okay, so the point is if you go to this constructor, the second constructor, so it is asking for a dict file, it is asking for a patch, mesh, and dict file, and it is asking for a value that is free stream value. So you have to assign this value because whenever this, for example, whenever this test case we run and we make the time object, and whenever this when we run it and uh, when we reach to the point when this library is called, it will make a constructor of this. So we have to pass a free stream value to the constructor. Okay. So you have to, and then it will make the object file. Okay. So we have to pass the required variable to the constructor and we have to give value of those variables. So we give the value of those variable here, that is free stream value. So this will be passed to the constructor. So what will be passed to the constructor? These things. That is the patch the mesh, dimension field vector volume mesh, and this is the dictionary file in which will read this file, free stream. So you have to think like this in open form. That will, so this is just a beginning. You'll learn a lot of things in this. This is just the beginning of how to change things. So now this is done. Okay. So now what we will do, now we can simply just run it. We control dict simple form. We'll just run simple form. It is done. But if you just to show you, if you don't define the libraries here, what kind of error you'll get? These are the important things. It is saying that what it is saying that these valid patch field types are this. It is saying there is no patch field my freestream velocity. All right. So valid patch field types are these 85 patch field that you can define. So if you if you do not write this, you not like call these libraries in the control dict file, it will not identify your customized boundary condition. If you do, it will simply give you this. Now, similar to this, if you like comment this free stream and run it, you should always try and do these kind of things because these things will get into your mind for a long time and it is a better way of learning by debugging the errors. So it is saying keyword free stream value is undefined. And you see, if we do this, this is done. All right, so this is how we change the bond. We'll look into the para form. You see, this is free stream boundary condition. So this is just the basic of boundary condition, how to change it, and and like where these boundary conditions are. You can see in finite volume in function objects, not in function object. Function objects are for the part in this in fields. We have patch fields, and in this case, we have everything. And like when we'll go for the advanced boundary condition, in which we will change the time and the space also, then we will go in depth of these boundary condition. So you see these basic fixed gradient, fixed value, mixed slice, transform. These all are the classes of the bond types of boundary condition. For example, this mixed. When we look at this mixed, okay, mixed FP patch field. All right. So this FP patch field is being used in these derived classes. For example, if you look at this fixed profile, so this fixed profile and this .h file, corresponding .h file also, this is using fixed value patch field. It is using fixed value patch field, not mixed value. So the file that we have changed is using mixed FP patch field. All right. So so the files, so the boundary conditions that are in this derived case, okay, are using some of the code from these basic. So every boundary condition is derived from the basic boundary condition. All right. So, and these basic boundary condition code is used in making these derived boundary condition. For example, if you take any boundary condition, let's say no slip boundary condition, if you go to this C file and .h file. So this is how you define it. All right. And this is using the basic boundary condition of fixed value FB patch field. Okay. Fixed value means it will not change with time. It is something like that. So if you want to know, you want to go into depth of what each basic boundary condition does, you can like go into these things. Now what we will do is we'll quickly go to this case. That is how to define a parabolic boundary condition in 2D channel. So because this is not changing with time, I think it is a fixed value boundary condition. So we can like So you can, in the derived file, you can take any of derived file, okay, and you copy it, paste it, do the similar thing that I have done, change it according to your what you want to give, and then you like change it according to you. So the one thing that is the people who want to work like more work like their research, do their research in open form, research project in open form. For them, I want to suggest that you also have a one form extend version with you always. For example, in this open form version, the form extend version, there are a lot of things which even have bugs, a lot of bugs in it. So they put everything in form extend, and in for open form part, we have things which are more bug free or which are more standard. So, so for example, I have form extent in my folder in my PC. So in form extent, if you go to the same, the like the structure of the form extent and open form is both is the same. There is no change. So if I go, I have form extent 3.2. If I go to finite volume fields, FB patch field derived, there is, you see, there is a parabolic velocity profile. So I want to, so the last test case was to use to simulate this parabolic velocity profile. Okay. So the form extent has parabolic velocity profile, but not this basic open form version. So form extent have a lot of things that there are not present in this normal open form version. So let's look at this file. So this is using fixed value FB patch field. Okay. So means the basic boundary condition code that it is using is fixed value FB patch field. And this is how it is done. So for example, in this case, it is this is calling a constructor, and this here it is initializing everything. So for parabolic boundary condition, we have view max, we have a height like maximum minimum, and we have a direction of parabolic velocity profile. So we have a normal vector, we have direction, we have u max. All right, and this is y, and this is normal vector of the direction of the velocity. This is y direction, and this is, so here we are initializing everything. So when this constructor is called, everything is initialized by default. And then these are the things we are here we are calling. So this is kind of mapper thing, I don't know what it is. And this here we are calling dict file. So it will, so when this constructor is called, most of the time this constructor is called, it will look for the dict file. It will tell to look for the dict file these things, what max value, n, that is the normal vector, and this y directional velocity. Okay, then this is also calling it. Okay, then these are all constructor. Then this is the main member function. So you can see you have here. Drink some water. You can see here that this is the main function where it is updating the parabolic boundary condition. Okay. But this is in form extent version. So this is where this code is the main source code, like which is updating the boundary condition. So same thing we will do. What we will do is copy this, okay, and take this to our folder. Where take this to our folder here uh, in the libraries, and copy this and do the same thing, compile it, and in the and then we'll run a test case. But to save the time, I have already made, I have done all these things. Like I have copied this and then change bit by bit everything. The main things that are changed when we like go from form extent to open form or form open form version 5 to 7 is the main thing that changes is this one. So main thing that changes is these files, that is include files. These are the things that changes usually. So you have to, so whenever you're switching between versions and form extent to open form, you have to make sure that you are including a correct libraries to compile that. Okay. So I have already compiled this my velocity. If I do wmake, this is saying this is unused variable, so it's okay. Like there are a lot of redundant things when we copy folder from one a folder to another. So this is already compiled, and the name of the library is lib my velocity. Okay. So if you go to lib platform libraries lib my velocity.so you can see here. Okay, so you see know that it is compiled and it is available to use. Now we'll go to the test case, same test case. We'll go to the same test case, pitch daily case. So this is not the pitch daily case. I have changed the mesh to make it like flow in a cylinder or flow in a channel. I have changed the mesh. This is not the pitch daily case. Now we'll go to system. So everything remains same. There is no change anywhere. So because there is change that need to be done in control dict file, but you know that I have already defined lib my velocity.so in this. So this is the part you don't want to miss, because otherwise you'll not be able to call your libraries during the runtime. Another thing that you have to change is this. Okay. So if you look into the .c file, what are the things that you have defined is max value n and u. All right. These are the things you have define. So you have to go to the constructor which has the dictionary, that is constant dictionary and dict, in which you have max value. You have L and you have Y. So what you do is first you look what kind of first you look for the type of boundary condition. So the type is my velocity. Okay. What we do is we go to U instead of my free stream, we do the type is my velocity. Then you know that then you go to this the constructor which is calling the dictionaries. It means it is looking for the variables that needs to be assigned in the dictionary. One thing is we have max value. So max value we want to give. So max value is a scalar, so we will give 2. Next is dict lookup and n is so just make sure. So scalar umax is scalar, do y and both are vector. So just quickly do it. One is n, another is y. One is n scalar and the velocity direction is in x direction. Okay. Another is y. The y direction is y, this one. Okay. Now I've changed our boundary condition. We'll rerun the test case again that we have already done for the constant velocity boundary condition. Where is it? Okay. It's daily. First form clean. Let's not do it. Uh, Simple form. Umax is not is undefined in the dictionary. Okay, one second. Yeah, yeah. So the name is not is max value. One second. So you have to define it like Umax. It's not the. Okay, okay. Sorry. So this I was looking at the value, the folder of form extent. You see, it is different. So it is saying max value. It is not max value. It is so it is what? This is the folder. You see Umax. That's why it is giving us an error that Umax is not there because I was looking into the wrong folder. Normal is not defined in the dictionary. Okay. Y and normal. It's not n, it's normal. Normal. I hope sequence doesn't matter. It's run now. Now we'll go to paraform. Look for the velocity. And you can see your parabolic velocity profile. And you can extract this using that simple graph dict file that you have if you want to plot a line plot. And the last, you see, this fully developed flow. This is fully developed flow with the uh, like parabolic velocity profile. So the velocity profile is being changed in downstream because we are providing non. Yeah, that's it. Okay, so these are the things. So I think it is this much for now. So for this, for if you want to look at the velocity profile, if it is like so, let me give you some information about the source code. This is so the things that the velocity profile is being calculated in this update coefficient. Okay, so why how it is doing is so it is calling a bounding box bb patch dot local points. So the for every for for the patch it is defining a bounding box. Okay, then so the point of this is to find the maximum and minimum value of the y direction. Then it is defining a vector that whose name is mid chord, and we are defining zero point 0.5 is equal to bb dot max plus bb dot min. So it is uh, the center of the y direction. Then it is calling every so cf is the control volume center of each face, and it is defining yc. It is defining this yc y. All right. After that. After that y this h is defined from here, so bb, that is the bounding box, the maximum of bounding box minus the minimum of the bounding box gives us the value of h, this h. And then the scalar field temp 1 it is calculating, and then umax x 1. So this is simply the what it is coding. Okay, so whenever you have to are going to change the boundary condition, you can always delete these like mapper things or clone things. I don't know about the clone, but some of the things these are some of these things are redundant that you can delete. So you can always look which are the important things by deleting them and see if it is running or if it is throwing an error, and if it is throwing an error, what is the error. So most of these files are redundant, so this also seems of no use. The most important parts are files are this one, and the update coefficient is where everything is being done. Okay, and for the same tutorial case you can use simple like simple graph utility that we have used previously to to plot the velocity profile at the front line. Okay, the left boundary condition if you want to see. So anyone has any question, please ask us right now. So there are a lot of questions, but I was not able to say it. Okay. Yeah, so these are advanced things. So we'll if you have any doubt for this, Pratyush is clear things out in the next. So the bonding box is more of I think so these things are mostly what I'll tell you is if you want to look into, you can ask Pratyush tomorrow, but these are the things which are defined in the surface fields. FV patch filed or these library that you see here, the library that you see here that are included in it, these provide with the code that we can directly define bonding box. Okay. So we have constructor for bonding box separately. So whenever we are defining these libraries, whenever we are defining these libraries or calling these libraries, we can use each and every function of uh, a function or parameter that is defined publicly in these header files or these libraries. Yes, yes, yes. Buju Shrestha. Okay. So I have, so it is, so I can show you, but it is already 10 p.m. So there is no change. If you look, let me just show you. So this is OpenFOAM parabolic profile that we have made. And this is from foam extent. All right, one second. This is from parabolic velocity profile from foam extent. So if you look at, if you compare these two files, there is no change at all. So the change will be uh, volume field, surface field. So there is no change at all. You can directly copy and run it. So whenever you face an issue, the issue will be in the issue will be in this make file. So the issue will be in make file. Yes, yes, form extent. So form extent is basically raw version of OpenFOAM. It is like it is simple. Form extent is also a version of OpenFOAM, but it is raw version in which there are a lot of solver which are which are not standard. So form extent have wide variety of things you can do as compared to OpenFOAM. Yeah, yeah. Sorry, sorry, sorry. My screen was not shared. Uh, Form extent installation is a little bit different from the. It is also very sometimes gets difficult. Yeah, I can we can show you in the future part when you'll do your project. We will install everything that is needed to complete your project. Yes, yes. Uh, Jamshid, I copied from Form extent to Open Form 6. So let me share my. I think I am visible now. You see this. This is Form extent 2. Jamshid, look here. This is Form extent 2. In this, I have not copied it, but I have done it like that. Jamshid, you can do it. Like I can do it right now. It's big issue, but it will take time. So no, no. So if you don't have a form extent, Buju Shrestha, if you don't have a form extent, you can always go to the Google, type it, and you'll get the GitHub library where you can find the case. So for example, I'm typing form extent for let's say form extent 5. So this is the source code. So this is release node of form extent 4.0. You see all the files are available here. So if you want to look at the src file, uh, so you can always download this and look at your cases. You don't need to install it because the source libraries are always available here. So the finite volume, and in finite volume we have fields, and we have fp patch fields and basic constraint derived, and we have tried this here. You see, here is parabolic velocity profile. So if you want to test it, you can get it into like you can always go to Google and you can go to GitHub and access those. You can download it and keep accessing it. Yes, yes, I will do. Nothing is compatible in OpenFOAM. If you using OpenFOAM 5, 6 is compatible, 7 is are more or less compatible. But if you're using even OpenFOAM version 2 and 10, there will be a lot of issues sometime. Usually, the if Courant number is less than 1, uh, should be okay. But even if the Courant number is very less than 1, you always have to show the time independent study. This is how it is done in research mostly. But if Courant number is less than 1, it should be enough. You should do the both to get your paper published. I have not seen the cases when Courant number is 1, less than 1, and it is giving you problem because of the time step. But things can happen. It is based on the your numerical method, the stability, the scheme that you are using. There are a lot of variables when your code diverges, and you sometimes don't know why it is happening. So, but for your question, yes, Courant number is more than enough. I was looking for some question. Any other questions? So you can always talk, man. You don't need to type. Like we can have interactive discussion also. We are only 7 or 6 guys here.
So what is the agenda of tomorrow's class?
So the agenda of tomorrow class will be will cover this paraboloid boundary condition, and will go into more into the compilation of libraries. Along with the boundary condition, we'll look into more depth into the compilation of libraries.
Okay.
Mhm.
Okay. Thanks, Rahul.
Yeah, yeah. So, like, if you have any question in this, first practice these test cases. And I know there are a lot of questions because in open form, like if you look here, there are too much code to understand. So if you look at the first glance at this code, this is too much to understand. And this is very high level C++. So at first glance, you can understand simple. This is constructor with the quality of polymorphism. That is, it can have different inputs. So you should focus on what you want. You should focus on the constructor which has dict file. And I don't know what the I even I know you should ask Pratyush in details about these things. This mapper, like how this mapper is done, what is the cloning part. So the code that you see, don't try to understand everything in first. Try to understand how to use it and what are the important changes that you need to do.
One more thing I wanted to ask
Mhm.
regarding the variables and underscore is there. Why underscore is there, right?
Yeah, so this is how the syntax of open form is.
Okay. So that
So if
signify that
Mhm.
characterizes the vector, right?
No. It is so if you are using any library or application and you are in basically it is done in libraries only. If you are defining a variable library which need to be uh, read at from the dict file during the runtime, you have to add that underscore.
Okay. Okay.
So
Okay.
this is kind of syntax of the open form. Like we don't have much in it, so this you have to add it. Yeah. So the variable that needs to be read from the dict file, you have to do this only to those. So you can always define inbuilt variable in the application like scalar this, scalar this, that is okay. For that, you need not to define underscore. For libraries compilation, it is like this only. Yes. So when we will go to the project part, home extent will come, don't worry. But first, you should be familiar with each and every aspect of how to, like basic aspect. Most of the people lacks the basic aspect. And this is my personal experience because you can try, go try doing big things, but you lack basic things. You'll never go ahead. You'll stuck at one point, and after that, you will be like, I can't do this. Any other question? Would you say stay typing something? No, no, it is not hard. So that the thing that is hard is when you go to the inside the OpenFOAM code. So if you want to run something that you can do using the test case, then it is simple, and the most of the people are able to do it. But when you go into the coding part inside the library, changing application, changing libraries, it is little bit hard, yes. And in starting, I suggest you learn C++. That will help. Like basic aspect of C++, classes, object-oriented programming. Yeah. So actually, yeah, these kind of things happen. So you have to stick to one version. Yeah. So Bhuju Shrestha, so whatever your project is, whatever your project is, you learn in that way. Like be focused, whatever you're learning, try to implement in your project. And at the last, when we'll be focusing on project specific things, then we'll interact one to one, 1v1, and then you can learn much better in these things. These things come with experience. Yeah. So when you switch between versions, other guys are there like this guy, K Saurav, Akshay Cool. Are you listening? Just give me a hi by turning on your mic. They are not here. Great, 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 great. Any questions? It's 10:20. I'm already tired from the whole day. Okay, so we'll end this session. So I'll be sharing these. All right, Subin. I'll be sharing all these cases. Please test. I will suggest you again if you want to move ahead in the session ahead, you want to catch up properly. Do not forget to practice these cases. I will put all these cases ASAP. Like by tonight, in the next 2 hours, I'll put the cases in the teams. Download these cases, use this, and the best thing is to practice is like I have done, like copy from here to here. If you're directly running the cases, it will not give you the intuition of how to do things. It might run for that time, but you will not get the intuition. Okay, good morning, Shrestha, and it's good night from my side. Well, stop sharing. That's all for today. Thank you for joining. Great.